Right now, you're trapped. Caged inside an invisible prison, moving at 186,000 miles every single second. That barrier circles Earth 7.5 times before your heart completes one beat. It crosses the distance to the moon in barely over a second. When sunlight leaves the sun's surface, it slams into your face 8 minutes later. Sounds unimaginably fast, doesn't it? Here's the truth that keeps physicists awake at night. On the cosmic scale, light speed is torturously, agonizingly slow. To cross our own Milky Way galaxy from one edge to the other takes 100,000 years at light speed, 100,000 years of traveling at the fastest speed physics allows, and you still haven't left your home galaxy. Think about that for a moment. The most powerful force we know, light itself, crawls across space like a wounded animal, and we're about to discover why the universe designed it this way. Why reality built an unbreakable wall, why every attempt to exceed this limit doesn't just fail it, reveals something terrifying about the nature of existence itself. If you like what comes next, hit the like button and subscribe. What you are about to witness will change your view of the night sky forever. The data is real. The timeline is set. We begin now. Let's make this real. You're standing on Earth right now. A photon of light races past you at 186,000 miles per second. In that single second, it could wrap around our planet's equator 7.5 times. That's incomprehensible velocity by human standards. We build machines that travel thousands of miles per hour and call them fast. Light laughs at our fastest rockets the way a hurricane laughs at a candle flame. But zoom out. Step away from Earth, away from our solar system, away from our local neighborhood of stars. Suddenly, that incredible speed becomes a cosmic joke. The nearest star system, Alpha Centauri, sits 4.3 light-years away. 4.3 years of continuous travel at maximum universal speed just to reach our closest stellar neighbor, Mars. We can see it with our naked eyes. It feels close. But even Mars, at its nearest approach, requires light over 3 minutes to arrive. 3 minutes for information to cross what seems like a short gap in our solar system. The Andromeda Galaxy, our nearest large galactic neighbor, hangs 2.5 million light-years distant. 2.5 million years. Civilizations rise and fall in less time. Species evolve and go extinct faster. Human beings didn't exist 2.5 million years ago. We were something else entirely. And light that left Andromeda back then is only reaching us now. Today. This moment. Would you board a ship knowing you'd never arrive at your destination within any meaningful human time frame? Would you sacrifice not just your life, but thousands of generations of lives, just to cross the cosmic void? The universe doesn't care about your timeline. It moves at its own pace. And that pace is maddeningly, impossibly slow when measured against the distances between stars. Scientists calculated these numbers over and over. They hoped for errors. They prayed for mistakes. But the mathematics held firm. The universe built itself with distances that mock our fastest possible speed. It's almost as if reality designed a cosmic joke specifically for intelligent beings. Here's the ability to think, to dream, to wonder about distant worlds. And here's the speed limit that makes reaching them impossible. Einstein's discovery and the mass-energy relationship. A 26-year-old patent clerk in Switzerland published a paper that shattered humanity's understanding of reality. His name was Albert Einstein. His equation became the most famous formula in physics: energy equals mass times the speed of light squared. Most people hear that equation and think about nuclear bombs, about the sun's fusion reactions, about converting matter into energy. But buried inside that elegant formula lies something far more sinister, a prison sentence for every massive object in the universe. Because that equation doesn't just describe energy conversion, it describes why nothing with mass can ever reach light speed. Here's what happens when you try. You're in a spacecraft. Call it Icarus. You fire your engines. At low speeds, everything behaves normally. Newton's physics works perfectly. You push harder, you go faster. Simple cause and effect. More fuel burned equals more velocity gained. This is the physics we know. The physics that feels intuitive. But as you approach 90% of light speed, something changes. The energy you're pumping into your engines doesn't translate to speed anymore. Not entirely. Instead, it converts into mass, into inertia, into weight. Your ship becomes heavier. Not because you're adding material, because energy itself becomes mass at relativistic speeds. At 99% of light speed, your spacecraft's mass multiplies by 7 times heavier than when you started. Your engines strain against this new reality. They burn harder. They consume more fuel. But instead of accelerating proportionally, you gain less and less speed. The energy you add doesn't disappear. It can't. Energy is conserved. It transforms instead. It becomes mass. Pushed to 99.9%. Your mass multiplies by 22. At 99.9-9-99%, you've become as massive as a mountain. Your engines, no matter how powerful, push against effectively infinite inertia. Every additional fraction of a percent toward light speed requires exponentially more energy. And the final gap, the last infinitesimal distance between 99.9-9-9-9-9% and exactly 100%, that requires infinite energy, truly infinite, not really large, not more than we can currently generate. Infinite, impossible. The universe doesn't contain infinite energy. Therefore, reaching light speed with mass is forbidden. Not by human limitation, by the fundamental structure of reality itself. Scientists stared at these equations with growing horror. The mathematics was beautiful, elegant, undeniable, and it sentenced every massive object to speeds below light, forever. Einstein didn't just discover a speed limit. He discovered a cosmic law enforcement system that cannot be bargained with, cannot be reasoned with, and absolutely will not stop until you stop accelerating. CERN and particle accelerator experiments. Words on paper mean nothing without evidence. Theories crumble under experimental scrutiny. So physicists built the ultimate testing ground. Particle accelerators. Massive machines designed to push particles to the absolute limits of speed. And the results confirmed Einstein's nightmare scenario with terrifying precision. The Large Hadron Collider, buried 17 miles underground beneath the border between France and Switzerland, represents humanity's most ambitious attempt to reach light speed. Scientists there accelerate protons, tiny particles, 11 trillion times lighter than a grain of sand around a circular track. They pump enormous energy into these particles, energy that could power entire cities. Those protons reach 99.9-9-9-9-9-9% of light speed. Read that number again. 6 nines after the decimal point. They're moving so fast that they complete 11,000 laps around the 17-mile tunnel every single second. They're traveling so close to light speed that the difference seems negligible. Surely, scientists thought, Just a bit more energy would push them over the threshold, but it didn't. It couldn't. They increased the energy input. The protons gained mass instead of speed. They poured more power into the system. The particles became heavier, more resistant, more stubborn. The final 3 meters per second, the gap between 99.9-9-9-9-9-9% and exactly 100% light speed required more energy than exists in every star in our galaxy. Think about that impossibility. The most powerful machine humanity has ever constructed, consuming enough electricity to power a small nation. Pushing particles that weigh almost nothing cannot close the final gap, not because the machine isn't powerful enough, because reality says no. Physicists tried different particles, different energies, different approaches. Every attempt produced the same result. As particles approached light speed, they gained mass. That mass resisted further acceleration. The energy didn't disappear. It couldn't. Conservation of energy is absolute. But it refused to convert into additional speed. It transformed into mass instead, into resistance, into an unbreakable barrier. And this happens every single day, thousands of times, in particle accelerators around the world. The same experiment, the same result, the same cosmic middle finger from the universe telling us, you cannot pass. Would you keep trying, knowing that every law of physics stands against you? Or would you start looking for loopholes? The unbreakable wall built by the universe. Scientists hate limits. It's against their nature. Every barrier in history eventually fell. The sound barrier, broken. The 4-minute mile, conquered. The height of mountains, we climbed them. The depth of oceans, we descended. The edge of the atmosphere, we breached it. Humanity's entire story is breaking through impossible barriers and laughing at the old limitations. But light speed is different. This barrier doesn't yield to better technology. It doesn't crumble before human ingenuity. It doesn't care about our determination or our dreams. Because this barrier isn't built from human materials or human understanding. It's woven into the fabric of reality itself. Imagine a wall, not made of concrete or steel, made of mathematics, made of the fundamental laws that govern how energy, mass, space, and time relate to each other. You can't tunnel through mathematical certainty. You can't demolish equations with explosives. You can't negotiate with the structure of space-time. Physicists checked their calculations thousands of times. They worked through the night, fueled by coffee and desperation, convinced they'd find an error. Some mistake in the math, some loophole in the logic. But the calculations held. Einstein's special relativity predicted exactly what particle accelerators measured. The theory matched reality with such precision that it became impossible to deny. The speed of light isn't arbitrary. It's not like the speed of sound, which changes based on medium and temperature. Light speed represents the speed at which causality propagates through the universe. It's the speed at which information can travel, the speed at which cause can produce effect. And that speed, that fundamental constant, creates a boundary that nothing with mass can cross. Here's the truly unsettling part. The universe didn't build this wall to protect anything. It didn't construct this barrier with purpose or intent. The wall exists because of how reality is structured. Mass, energy, space, and time are interconnected in specific mathematical relationships. Those relationships inevitably produce a maximum speed. That maximum happens to be the speed of light. And that maximum is absolute. No amount of technological advancement changes this. Even civilizations billions of years older than ours, with technology we can't imagine, face the same barrier, the same mathematics, the same physical laws. Unless the fundamental structure of reality itself is different in their corner of the universe, and we have no evidence suggesting it is there, trapped just like us. This realization haunts physicists. It's one thing to face an engineering challenge. Challenges can be solved with clever designs and better materials. It's entirely different to face a law of nature that explicitly forbids your goal. That's not a challenge to overcome. That's a fundamental statement about what's possible and what isn't. And light speed sits firmly in the isn't category. The beginning of searching for alternative paths. So we're trapped. Massive objects cannot reach light speed, cannot exceed it. The mathematics is ironclad. The experimental evidence is overwhelming. The particle accelerators confirm it daily. We've slammed into a cosmic brick wall at 99.9-9-9-9-9% of our maximum speed, and there's nowhere left to go. But here's where human stubbornness becomes interesting. When told something is impossible, we don't give up. We look for loopholes. We search for technicalities. We ask, okay, that specific approach doesn't work. What about a different approach? Einstein said, nothing with mass can reach or exceed light speed by accelerating through space. Fine. What if we don't accelerate through space? What if space itself moves? What if we manipulate the fabric of reality instead of pushing against it? The speed limit applies to objects moving through space, but does it apply to space itself? These questions opened new avenues of research. Physicists began exploring solutions to Einstein's field equations that seemed bizarre, impossible, ridiculous, but mathematically valid. If the equations allowed certain exotic conditions, maybe those conditions could be engineered. Maybe there's a way to sidestep the barrier rather than crash through it. This shift in thinking represents humanity at its finest and most dangerous. We're told no by the universe itself. We're shown mathematical proof that something cannot be done. And our response? Challenge accepted. We start looking for the fine print, the exceptions, the clever workarounds that technically don't violate the letter of the law while completely ignoring its spirit. But finding a loophole and exploiting it are vastly different challenges. One requires creativity and mathematical skill. The other requires technology we don't possess, energy sources we haven't discovered, materials that may not exist. And even if we overcome those obstacles, we'll face consequences we barely understand, because the universe didn't build that barrier for no reason. Speed limits exist to prevent catastrophe. What happens when we find a way around the cosmic speed limit? What does the universe do when we cheat? We're about to discover that breaking the ultimate barrier doesn't just let us go faster. It breaks something far more fundamental, something we didn't even realize could break. And once it's broken, there may be no putting it back together. Are you ready to see what happens when we tear apart the rules of reality itself? Right now, somewhere in the universe, time is moving at a different speed than it is for you. Not metaphorically, not philosophically, literally, two clocks, perfectly synchronized, separated by velocity, tick at different rates. One races ahead, the other falls behind, and the gap between them grows wider with every passing second. You've just learned that light speed creates an unbreakable barrier, but here's what nobody tells you about approaching that barrier. The journey itself tears reality apart. Before you even reach the impossible limit, the universe transforms around you. Time becomes your enemy. Space distorts beyond recognition, and the people you left behind. They age into dust while you experience a single afternoon. Welcome to the consequences of moving fast. Really fast. This is where physics stops being abstract and becomes visceral, personal, devastating. The Doppler effect and the universe's visual transformation. You're in your ship. Let's call it Icarus, same as before. You've somehow managed to accelerate to 99% of light speed, not quite the barrier, but close enough that reality starts breaking down. You look out your window, expecting to see stars. What you actually see is nightmare fuel. The stars ahead of you shift color. They start as white pinpoints, like you've always known them. Then they bleed blue, deeper blue, violet. Then they vanish entirely, disappearing into invisible ultraviolet radiation your eyes can't detect. The entire forward view compresses into a brilliant, blinding sphere of light directly ahead. Every star in that direction gets squeezed into an impossibly bright focal point. Behind you, darkness, complete, total darkness. The stars don't just fade, they drain of color, bleeding from white to yellow to red to deep crimson, then wink out of existence entirely. They shift into infrared wavelengths your eyes can't perceive. The universe behind you becomes an infinite void, an expanding emptiness chasing you through space. This is the Doppler effect on a cosmic scale. You've heard it with sound. An ambulance siren shifts pitch as it passes you, approaches, higher pitch, recedes, lower pitch. Same principle applies to light, but at relativistic speeds, the shift becomes extreme. Wavelengths compress ahead, stretch behind. The visible spectrum gets crushed into a narrow tunnel directly in front of you. You're flying through a corridor of distorted reality. The universe, Unuther, 360-degree sphere of stars. Surrounding you collapses into a bright disk ahead and absolute blackness everywhere else. Navigation becomes impossible. Reference points vanish. You're flying blind through a cosmos that refuses to look like itself anymore. And this happens before you even approach the true barrier. This is just 99%. Imagine 99.9, 99.99. The distortion intensifies. The bright sphere ahead contracts further. The darkness behind expands. You're racing through a universe that's actively trying to hide itself from you. Would you trust your senses in this distorted reality? Or would the visual chaos drive you mad long before you reached your destination? Because what's happening outside your window is nothing compared to what's happening to time itself. The time dilation phenomenon. Here's where everything you understand about time shatters. You're in your ship, moving at 99% of light speed. You check your watch. 1 hour passes. You sip coffee. You read a book. You feel time flowing normally, because for you, it is normal. Time always feels normal in your own reference frame. That's the cruel joke Einstein discovered. But back on Earth, 1 hour for you equals 7 hours for everyone else. Your children age 7 times faster. Your parents grow older. Your friends move on with their lives. While you experience 60 minutes, they live through 420 minutes. 7 hours of their reality compressed into 1 hour of yours. This isn't a trick. It's not an illusion caused by light, delay, or communication lag. Time itself genuinely runs slower for you. Physicists hate calling it time dilation because it sounds like time is stretching or expanding. It's worse than that. Your time is running at a fundamentally different rate than everyone else's. You're not just experiencing time differently, you're experiencing different time. In 1971, scientists wanted proof. They took for atomic clocks, the most precise timekeepers humanity could build, and placed them on commercial airplanes. 2 clocks flew eastward, 2 flew westward, 2 more clocks stayed on the ground as controls. After the flights completed, they compared all the clocks. The airborne clocks ran slower than the ground clocks. Not by much. We're talking billionths of a second. But measurably slower. Undeniably slower. The clocks traveling through the air experienced less time than the stationary clocks. Einstein's equations predicted the exact difference. The measurements matched perfectly. Time genuinely runs at different speeds depending on your velocity. But airplanes move slowly compared to light speed. The effect is tiny, negligible, barely noticeable. Now scale up. Push to 99.9% of light speed. 1 hour for you equals 22 hours for Earth. At 99.99%, 7 days pass on Earth for every hour you experience. 7 complete rotations of the planet. 168 hours of Earth time compressed into your single hour. Think about the human cost. You launch on your journey. You wave goodbye to your 10-year-old daughter. The trip takes what feels like 6 months in your reference frame. You return home, expecting to find your daughter slightly older. 11 years old, maybe. Instead, she's 70. An old woman. She lived her entire life, childhood, adolescence, adulthood, old age, while you experienced half a year. Your parents, dead. Your friends, elderly or gone. Your career, obsolete. Technology advanced decades beyond what you remember. Culture shifted. Language evolved. Everyone and everything you knew transformed into something alien. And you're the same age you were when you left, unchanged. A ghost from the past, haunting a future that moved on without you. Scientists realized this creates a one-way time machine. Travel fast enough, and you jump forward in time. Not backward. Never backward, only forward. And there's no return journey. You can't slow down and reclaim the lost years. They're gone. Spent. The universe collected them as payment for your velocity. GPS systems and practical evidence. Maybe you're thinking this is all theoretical. Abstract physics that doesn't affect real life. Wrong. You prove Einstein right every time you use your phone's navigation app. GPS satellites orbit Earth at roughly 8,600 miles per hour. That's fast by human standards. Slow by cosmic standards. But fast enough that relativistic effects matter. Those satellites contain atomic clocks synchronized with atomic clocks on the ground. They need perfect timing because GPS works by measuring how long signals take to reach your phone from multiple satellites. Tiny timing errors create huge position errors. Here's the problem. The satellite clocks and ground clocks run at different speeds. The satellites are moving faster than the ground, so their clocks run slower. Time dilation. But they're also farther from Earth's gravitational field, which makes their clocks run faster. General relativity. These two effects partially cancel each other out, but they don't completely balance. Engineers had to program the satellites to account for these time differences. Without correction, the timing errors would accumulate. After just one day, your GPS position would drift 7 miles off your true location. After a week, 50 miles. Your navigation app would tell you you're in the next town over. Your turn-by-turn directions would guide you into fields and forests. Every single day, billions of people rely on technology that only works because we account for time dilation. The effect is real, measurable, necessary to include in our calculations. Einstein isn't some abstract theorist anymore. He's the reason your phone knows where you are. But GPS satellites move slowly compared to light speed. The time dilation they experience is tiny, microseconds per day. Now imagine pushing to genuine relativistic speeds. The effect doesn't scale linearly, it explodes exponentially. At 99.9-9-99% of light speed. 1 second for you equals over 700 seconds for Earth. 1 hour equals nearly a month. 1 day equals almost 2 years. You want to visit another star system. Even the closest one, Alpha Centauri, sits 4.3 light-years away. Travel at 99.99% of light speed, and the journey takes roughly 4.3 years from Earth's perspective. But for you, time dilation compresses that journey into just a few weeks. You experience weeks while Earth experiences years. Sounds like a good deal, right? Fast interstellar travel from your perspective. But here's the trap. You can never go home. Not really. Home exists for 0.3 years in the future. The Earth you left is gone. Everyone you knew has aged years, while you aged weeks. Your entire timeline has been ripped away from everyone else's timeline. You're a temporal refugee, displaced, lost in time. The Muon particle experiment. Maybe you still don't believe it. Maybe this sounds too bizarre, too impossible. Here's the experiment that proves time dilation beyond any doubt. An experiment that happens naturally, constantly, in the atmosphere above your head right now. Cosmic rays high-energy particles from space slam into Earth's upper atmosphere roughly 10 miles above the surface. When they hit air molecules, they create showers of new particles, among them muons. These particles are unstable. They decay quickly, incredibly quickly. Their half-life is roughly 2 microseconds, 2 millionths of a second. They fall apart almost as soon as they're created. Here's the problem. Even traveling at near light speed, a muon created 10 miles up shouldn't reach the ground before decaying. Do the math. 10 miles at near light speed takes way longer than 2 microseconds. The muons should disintegrate high in the atmosphere. They should never touch the surface. Detectors on the ground should register 0 muons, or maybe a few lucky ones that somehow survived longer than expected. But we detect thousands of muons at ground level every second, everywhere on Earth. They rain down constantly. They shouldn't exist by the time they reach us, but they do, in huge numbers. Something is wrong. Either our understanding of muon decay is completely broken, or something else is happening. Time dilation. The muons travel so fast, 99.98% of light speed, that time slows down for them. From our perspective, they should decay in 2 microseconds. But from their perspective, time runs slower. Those 2 microseconds stretch into longer periods. They live longer, not because they're more stable, because their clocks tick slower than ours. From the muon's reference frame, it exists for only 2 microseconds, just as expected. But during those 2 microseconds of Muon time, significantly more time passes for us. Enough time for the particle to cross 10 miles and reach the surface before its internal clock runs out. The muon doesn't know it's living longer. From its perspective, everything is normal. It's the outside universe that's racing ahead. Scientists can measure this. They place muon detectors at different altitudes: top of mountains, sea level, deep underground. The number of detected muons decreases with depth, exactly as predicted by time dilation calculations. The math works perfectly. The measurements match the theory. Time genuinely runs at different speeds for objects moving at different velocities. This isn't speculation. It's not theoretical physics confined to textbooks. It's happening right now, above your head. Particles are experiencing different time than you. They're living proof that time is not absolute, not universal, not the same for everyone. Your time and my time only match because we're moving at similar speeds. Change that velocity, and our times diverge permanently. Personal sacrifice and existential consequences. Now, let's make this personal. Strip away the equations and the experiments. Focus on what it means for a human being. You, someone with family, friends, a life, dreams, connections to other people who exist in the same timeline as you. You're offered a mission. Travel to a nearby star system. Study potentially habitable planets. Expand humanity's knowledge. Become an explorer, a pioneer. The journey takes 10 years from Earth's perspective, but you'll travel at 99.95% of light speed. For you, the journey takes only 1 year. You'll age 1 year while Earth ages 10. Think about that decision. Really think about it. You say goodbye to your partner, your children, your parents, your friends. You promise to return, but when you come back, they won't recognize you. Not because you've changed, because they have. A decade of life happened without you. Your children became teenagers. Your parents became elderly. Your friends moved to different cities, got married, had kids of their own. An entire decade of experiences, memories, and changes that you weren't part of. And you remember the goodbye like it was last week. Because for you, it was 1 year ago. You haven't grieved the time loss because you didn't experience it, but everyone else did. They mourned your absence. They moved on. They had to. Life doesn't pause just because one person left. Now imagine a longer journey, 20 years from Earth's perspective, 50 years, 100 years. You could board a ship, experience what feels like a few years of travel, and return to find everyone you've ever known is dead. Your grandchildren are older than you. Your great-grandchildren are elderly. The world you left behind exists only in history books. You're a time traveler who skipped forward through history without meaning to. This is the true curse of relativistic travel. Not the energy requirements, not the engineering challenges, the temporal isolation. You can visit distant stars, but the cost is everything and everyone you care about. You become unstuck from your own timeline, a wanderer between eras, forever young in a universe that refuses to wait for you. Some philosophers argue this makes us prisoners twice over. First, we're trapped below light speed by the laws of physics. Second, approaching light speed exiles us from our own time. We can't reach distant stars quickly enough to matter, and trying anyway destroys our connections to home. The universe doesn't just limit our speed, it punishes us for trying to circumvent that limit. Picture yourself at the moment of decision, standing at the airlock. 1 step forward means losing everyone behind you. 1 step backward means staying trapped on Earth forever, wondering what could have been. Which choice haunts you more, the people you'll lose, or the stars you'll never see? The universe forces you to choose between your timeline and your curiosity, between the people you love and the places you dream about, and there's no compromise, no middle ground. Accelerate toward the stars, and time rips you away from everyone else. The faster you go, the more violent the separation, until eventually, at the ultimate speed, time stops entirely, and you cease to exist as anything recognizable. What happens when time itself freezes? When your speed becomes so great that thinking becomes impossible. When you reach the point where consciousness ends. That's where we're going next. To the speed where everything breaks down, where existence itself becomes questionable. Where we ask, if you reached light speed, would you still be you? Or would you become something else entirely? Right now, photons are racing across the universe at the maximum possible speed. They've traveled for billions of years from distant galaxies. They crossed impossible distances. They journeyed through the vast cosmic void, and from their perspective, the journey never happened. They experienced nothing. Zero time, zero distance, instant arrival from the moment of creation to the moment of destruction. You've learned that approaching light speed distorts the universe and tears you from your timeline. But that's still below the barrier. Still in the realm where physics bends but doesn't break completely. Now we're asking the forbidden question. What happens at exactly 100%? What does existence look like when you finally reach the ultimate limit? The answer is terrifying. At light speed, mathematics tells us that time stops completely, totally, permanently. You don't just experience time differently. You stop experiencing anything at all. Welcome to the speed where consciousness ends. The complete collapse of physics at 100%. You've been accelerating. 90%, 99%, 99.9%. Each increment harder than the last. Your mass multiplying. Your energy requirements exploding. But somehow, through some impossible means, you've acquired infinite energy. You're about to cross the final threshold. 100% of light speed. Exactly what does the universe look like in that final instant before you breach the barrier? The visual distortions you experienced at 99% intensify beyond comprehension. The bright sphere ahead compresses to an infinitesimal point. A singularity of light directly in front of you, behind you. Not just darkness, absolute nothingness. The entire observable universe collapses into a single geometric point. But you never see what comes next, because at exactly light speed, the equations break down. Division by zero appears in the mathematics. Infinities emerge everywhere. The Lorentz factor, the term that describes time dilation and length contraction, approaches infinity. Time dilation becomes infinite. Length contraction becomes complete. The universe ahead of you contracts to zero distance. The time required to cross any distance becomes 0 seconds. Physicists stare at these equations with a mixture of fascination and dread. The math doesn't just suggest something weird happens. It screams that reality itself becomes undefined, impossible, meaningless. The numbers stop making sense because the concept stops making sense. You can't exist at light speed with mass. Not it's really hard. Not we don't have the technology. You cannot exist. The universe forbids it at a fundamental level. Think about what infinity means in these equations. Infinite time dilation means time stops completely, not slows down dramatically, stops. Infinite mass means you become infinitely heavy. Infinite energy means you'd need to consume infinite fuel. These aren't engineering problems with engineering solutions. These are mathematical impossibilities. They're the universe's way of saying this state of existence is forbidden. But let's ignore the impossibility for a moment. Let's pretend you somehow circumvented every physical law and reached exactly light speed. What would you experience? What does existence feel like when time stops? Nothing. You'd experience absolutely nothing. Because experience requires time to flow. Thoughts require time to form. Perceptions require time to process. Consciousness requires time to exist. At zero time, there is no thought, no perception, no consciousness, no you. You'd be frozen in a single eternal moment that never progresses forward. A photograph of a person rather than an actual person. Would you even be alive at that point? The question becomes philosophical rather than physical. If your neurons can't fire because time isn't flowing, are you dead? Or are you something else? Something suspended between existence and non-existence? A quantum ghost trapped in the machinery of a universe that refuses to let you move forward. The photon's perspective on the universe. We can't reach light speed with mass. But something does travel at light speed, constantly, everywhere. Photons, particles of light. They're born at light speed and die at light speed. They never accelerate, never decelerate. They simply exist at the maximum possible velocity from the instant they're created until the instant they're destroyed. So what does the universe look like from a photon's perspective? Here's where physics gets truly mind-bending. A photon leaves a galaxy 13 billion light-years away, 13 billion years ago, long before Earth existed, before our sun formed, before our solar system was even a cloud of dust. That photon travels across the entire observable universe. It crosses vast voids between galaxy clusters. It passes through regions where space itself is expanding. It journeys for 13 billion years of cosmic time, then it reaches Earth. It strikes your telescope. It gets absorbed by a detector. It transfers its energy. It ceases to exist. From our perspective, that photon had an incredible journey. 13 billion years of travel. 13 billion light-years of distance. An epic voyage across space and time. From the photon's perspective, the journey never happened. The moment of its creation in that distant galaxy and the moment of its destruction in your telescope are the same moment. Simultaneous, instantaneous. The photon experiences zero time between birth and death. It doesn't perceive the 13 billion years of travel because, for it, those years don't exist. Even more bizarre, distance itself becomes zero from the photon's perspective. Length contraction at light speed becomes complete, infinite. The 13 billion light-years between the distant galaxy and Earth contract to zero distance. The photon doesn't travel across space because, from its reference frame, there is no space to cross. The starting point and ending point occupy the same location. Wrap your mind around that impossibility. The photon simultaneously exists everywhere along its path and nowhere at all. It's created and destroyed in the same instant despite 13 billion years passing from our perspective. It crosses 13 billion light-years of distance despite experiencing zero distance. These aren't paradoxes in the logical sense. They're accurate descriptions of reality at light speed. The universe genuinely works this way. Scientists sometimes joke that photons are the universe's way of proving that space and time are relative, that your reference frame determines your reality. But it's not really a joke. It's a profound statement about the nature of existence. What we call distance and duration are not universal properties of reality. They're properties of your reference frame. Change your speed, and you change your experience of space and time. Reach light speed, and space and time cease to have meaning entirely. Think about every photon of light you've ever seen. Sunlight warming your face, starlight reaching your eyes at night, the glow of your phone screen. Every single photon experienced zero time during its journey to you. From its perspective, it was created and absorbed in the same instant. Its entire existence lasted exactly 0 seconds. Yet from your perspective, those photons traveled for minutes, years, or billions of years. Which perspective is correct? Both. That's the unsettling truth. Reality doesn't have a single, objective timeline. Every reference frame experiences its own valid timeline, and at light speed, that timeline collapses to a single point. Past, present, and future merge into one eternal now that never progresses forward. Instant arrival at light speed. Let's push this concept further. Imagine you're a photon. You don't have thoughts or perceptions, but pretend you do for a moment. You're created inside the core of a star. Nuclear fusion releases you. You begin your journey outward through the star's dense plasma. From an external perspective, this journey takes thousands of years. Photons bounce around inside stars, getting absorbed and re-emitted countless times before finally escaping to space. But from your perspective as the photon, you're created and you arrive at the star's surface in the same instant. No journey, no duration, no experience of time passing. The thousands of years that external observers measure simply don't exist in your reference frame. You escape the star. You travel through space. You cross light years of void. You pass by planets. You navigate through asteroid fields. You eventually strike a planet's atmosphere. You get absorbed by a molecule. You cease to exist. From external observers' perspective, this journey took years. From your perspective, instant. Creation and destruction are simultaneous events with zero duration between them. This creates a bizarre situation. The entire observable universe, from a photon's perspective, is zero-dimensional. No length, no width, no depth, no duration. Everything that exists anywhere at any time collapses into a single point instant. The Big Bang and the heat death of the universe occupy the same moment and location. The birth of the first stars and the death of the last stars are simultaneous. All of space and all of time compressed into geometric nothingness. How can this be? How can the universe be both vast and empty from our perspective, yet vanishingly small and instantaneous from light's perspective? Because space and time are not fixed, universal properties, they're relative. They depend on your motion through space-time. And at light speed, that motion is so extreme that space and time lose all meaning. Now consider what this means for information. Information cannot travel faster than light. Cause and effect propagate at light speed. So in a very real sense, the speed of light is the speed at which the universe communicates with itself. It's the speed at which reality updates, and from reality's perspective, from the perspective of the information traveling at light, speed all updates happen instantly. No delay, no propagation time. The entire universe is in constant, instantaneous communication with itself, but only from light's perspective. From our perspective, trapped below light speed, information takes time to arrive. Light from the sun takes 8 minutes to reach us. Light from distant galaxies takes billions of years. We experience delays, propagation times. The speed of causality feels frustratingly slow because we're moving slowly compared to light. We're experiencing time instead of existing at the boundary where time stops. Would you want to exist as a photon? To experience everything and nothing simultaneously? To have your entire existence compressed into a single dimensionless point instant? Or is the slower experience of time the ability to think, perceive, and exist as a conscious entity worth being trapped below the ultimate speed limit? The consciousness and experience problem. Let's bring this back to something personal, something human. You're not a photon. You're a conscious being. Your brain consists of neurons firing in complex patterns. Thoughts emerge from electrical and chemical processes that require time to unfold. Memories form through physical changes in neural connections. Consciousness itself requires duration, requires sequence, requires one moment following another. So what happens to consciousness at light speed? If time stops, neural processes stop. Electrical signals freeze mid-transmission. Chemical reactions halt. The physical substrate that generates consciousness becomes static, unchanging, frozen like a sculpture rather than active like a living brain. Can consciousness exist without time? The question sounds philosophical, but it has physical implications. Consciousness requires information processing. Processing requires state changes. Changes require time. No time means no changes. No changes means no processing. No processing means no consciousness. At light speed, the very machinery that generates your sense of self stops functioning. Imagine being frozen in a single thought. Not for a second, not for a year, forever. That single neural configuration locked in place with no possibility of progression. You can't complete the thought because completing it requires time. You can't form a new thought. You can't perceive anything changing because change requires time. You exist in some technical sense, but you don't experience existing. There's no you to have experiences. Scientists debated this extensively. Some argued that consciousness might still exist at light speed, just in a different form we can't comprehend. Others insisted that consciousness definitionally requires temporal duration, making it impossible at light speed. But everyone agreed on one thing: if consciousness could somehow exist at light speed, it would be so alien to our normal experience that calling it consciousness might be misleading. Think about your own experience right now. You're reading these words. Each word follows the previous word. Your eyes move across the screen. Your brain processes the information. You form thoughts in response. All of this requires time, requires sequence, requires causality. You can't read the ending of this sentence before you read the beginning. That's not how information processing works in a universe with time. At light speed, all of that sequential processing vanishes. You'd theoretically perceive, if perception is even possible, everything simultaneously, beginning and end at once. All moments compressed into one. But what does simultaneous perception even mean? Can you think a thought that has no sequence? Can you process information that has no before or after? Can you exist without the ability to change from one state to another? The honest answer is, we don't know. We can't know, because consciousness is something we experience from inside. We can study brains from the outside, measure neural activity, map connections, but the subjective experience of being conscious is not something we can measure externally. And since nothing with consciousness has ever reached light speed, we have no data on what would happen. The existential prison of light speed. Here's where the full horror becomes clear. Light speed isn't just a barrier preventing fast travel. It's an existential boundary between two fundamentally different modes of existence. Below light speed, you experience time. You have duration. You can think, change, grow, experience. You're part of the causal flow of the universe. Above light speed, impossible. Forbidden by the mathematics of reality itself. At exactly light speed, you become something that exists but doesn't experience. A frozen artifact of matter and energy with no inner life. The universe built this barrier with terrifying precision. It placed the speed limit at exactly the point where consciousness ends. Not slightly above, not slightly below. exactly at the threshold where temporal experience becomes impossible, almost as if reality is saying, you can approach this speed, you can get incredibly close, but the moment you actually reach it, you cease to be what you are. You become something else, something that cannot think or feel or know that it exists. Some physicists find this comforting in a strange way. The barrier prevents us from accidentally destroying our own consciousness. We can't inadvertently accelerate into oblivion because the energy requirements become infinite before we reach the danger zone. The universe protects us from ourselves through sheer physical impossibility. Others find it deeply disturbing. Why does the universe care about consciousness? Why place the speed limit at exactly the point where experience ends? Is there some fundamental connection between the speed of light and the nature of conscious experience? Or is this just a coincidence? We noticed the connection because we're conscious beings contemplating the speed limit. The question remains unanswered, perhaps unanswerable, but one thing is certain. Reaching light speed with mass isn't just an engineering challenge, it's an existential threat. It's the difference between being and not being, between experiencing and not experiencing, between consciousness and something else. Something we don't have words for because we've never encountered it. Picture yourself at the threshold. One more increment of speed and you cross into the zone where time stops, where your neurons freeze, where the flowing river of consciousness becomes a static lake. Would you take that final step? Would you sacrifice your ability to experience in exchange for reaching the ultimate speed? Or would you stay below the barrier, forever wondering what lies beyond but unwilling to pay the price of finding out? But what if there's another way? What if we don't break through the barrier? What if we go around it? What if the universe left a loophole in its own rules? That's next. The trick that might let us exceed light speed without destroying ourselves. The mathematical possibility that sounds like science fiction but emerges from Einstein's own equations. The warp drive, the manipulation of space itself, and the exotic energy that makes it possibly or impossible. We're about to explore the one way humans might cheat reality and survive the experience. Are you ready to bend the universe instead of breaking it? Right now, somewhere in the universe, space itself is moving faster than light. Not objects through space. Space itself. Distant galaxies recede from us at speeds that exceed light velocity because the fabric of reality between us expands. They're not violating Einstein's speed limit. They're riding the expansion of space-time. And if the universe can do it naturally, maybe we can engineer it artificially. You've learned that reaching light speed destroys consciousness, that approaching it exiles you from your own timeline, that the universe built an unbreakable barrier preventing massive objects from crossing the threshold. But here's the loophole nobody tells you about. Einstein said, you can't move through space faster than light. He never said, space itself can't move faster than light. Welcome to the warp drive. The one theoretical method that lets us cheat reality without technically breaking the rules, and the exotic physics that makes it possible or keeps it forever out of reach. Cheating Einstein's rules. 94. A Mexican physicist named Miguel Alcubierre sat down with Einstein's field equations and asked a dangerous question. What if we stopped trying to push objects through space and instead moved space around the object? What if we could surf on a wave of space-time itself? The idea sounds like science fiction because it is science fiction. Star Trek's warp drive, faster than light travel without actually moving faster than light locally. But Alcubierre wasn't writing fiction. He was solving equations. Einstein's equations. The same mathematical framework that accurately describes gravity, black holes, the expansion of the universe, and every other large-scale phenomenon we've ever measured. And the equations said yes. Space-time can be warped in a way that moves an object from point A to point B faster than light could travel between those points through normal space, not by pushing the object through space, but by contracting space in front and expanding space behind. The object sits in a bubble of normal space-time, completely stationary within that bubble, while the bubble itself moves at any speed, including speeds far exceeding light. Think of it like this. You're standing on a moving walkway at an airport. You're not walking, you're standing still, but the walkway beneath you moves, carrying you forward. From your perspective, you're stationary. From an outside observer's perspective, you're moving. Now scale that concept up to cosmic proportions. Replace the walkway with space-time itself. Replace your walking speed with any velocity you desire, including faster than light. The Alcubierre drive creates this effect by compressing space ahead of your ship and expanding space behind it. Space in front contracts, bringing your destination closer. Space behind expands, pushing your origin farther away. Your ship rides the boundary between contraction and expansion like a surfer on a wave. You never accelerate. You never experience G-forces. You never approach light speed from your local reference frame, because locally, you're not moving at all. This solves every problem we've discussed so far. No mass increase, because you're not accelerating. No time dilation, because you're stationary in your local reference frame. No visual distortion, because light around you behaves normally. No consciousness problems, because time flows normally inside your bubble. You could accelerate to 1,000 times light speed, 10,000 times, 1,000,000 times, and experience none of the relativistic nightmares that plague conventional acceleration. It's the perfect loophole. Einstein's equations permit it. The mathematics is solid. The theory is sound. There's just one tiny problem. You need negative energy. Lots of it. More than exists in the solar system. Possibly more than exists in the galaxy. And we're not entirely sure negative energy can exist in the quantities required. The working principle of the Alcubierre drive. Let's get specific about how this works. Your ship sits inside a bubble of normal space-time. Call it a warp bubble. Inside that bubble, physics works exactly as you'd expect. You can walk around, drink coffee, read a book. Time flows normally. Space is three-dimensional. Cause and effect behave themselves. It's completely ordinary, but the boundary of that bubble, that's where reality breaks down. At the forward edge, space contracts. Not gradually, dramatically, violently. Space ahead of you compresses like an accordion being squeezed. Stars that were light years away suddenly become light years closer. Not because they moved, because the space between you and them shrank. At the rear edge, space expands. The opposite effect. Space behind you stretches like taffy being pulled. Your point of origin recedes rapidly, not because you're moving away from it, but because space itself grows between you and it. More space appears where less space existed before. The ship never crosses the boundary. It stays centered in the bubble where space is normal, but the bubble moves through space, or rather, space moves around the bubble at whatever velocity the field equations support, which could be faster than light, much faster, because the bubble isn't moving through space in the conventional sense. It's surfing on a wave of space-time geometry. Here's the beautiful part. This doesn't violate special relativity. Special relativity says nothing can move through space faster than light. The Alcubierre drive doesn't move through space. It moves space. That's completely different. It's like the difference between walking across a room and sitting on a chair while someone moves the room around you. You can argue you didn't really walk because you didn't move relative to the chair. Same principle here. The ship doesn't move relative to local space. Local space moves relative to distant space. From outside the bubble, observers would see your ship apparently moving faster than light, but measuring your local velocity would show 0. You're stationary, not moving, just sitting there while space flows around you like water around a rock in a stream. The rock doesn't move with the current. The current moves past the rock. Your ship is the rock. Space-time is the current. This creates bizarre situations. Imagine traveling to Alpha Centauri, 4.3 light-years away, with conventional propulsion at 99.9% light speed. The journey takes over 4 years from Earth's perspective and several months from yours due to time dilation. With an Alcubierre drive running at 10 times light speed, the journey takes roughly 5 months from both perspectives. No time dilation, no relativistic effects. Because you never actually moved fast. Space moved. You stayed put. You could push it further. 100 times light speed. 1,000 times. The field equations don't impose limits the way conventional physics does. You're not constrained by mass-energy relationships because you're not accelerating mass. You're warping geometry. Different rules apply. Rules that are simultaneously more permissive and more demanding. Which brings us to the catch. The requirements. The price the universe demands for this loophole. The need for negative energy and exotic matter. Every free lunch has a hidden cost. The Alcubierre drive's cost. Negative energy. Not just a little bit. Enormous quantities. Mind-boggling amounts. When Alcubierre first published his solution in 1994, the calculations suggested you'd need negative energy equivalent to the mass of Jupiter converted entirely into negative energy density. Let's pause on that number. Jupiter's mass is roughly 300 times Earth's mass. Converting that entire mass into energy regular positive energy would require E equals mc squared. The resulting energy would be staggering. Enough to power human civilization for trillions of years. Now convert that same amount into negative energy. That's what the original Alcubierre drive required for a warp bubble maybe 30 feet across. But what even is negative energy? We're used to positive energy, heat, light, kinetic energy, chemical bonds, mass itself. All positive. Negative energy is stranger. It's not antimatter. Antimatter has positive energy. Negative energy is energy that's somehow less than nothing. Energy that creates repulsive gravity. Energy that violates energy conditions physicists thought were fundamental. In classical physics, negative energy doesn't exist. Can't exist. Energy is always positive or zero, never negative. But quantum mechanics changes the rules. In quantum field theory, empty space isn't really empty. It's filled with virtual particles constantly appearing and disappearing. Particle-antiparticle pairs that exist for impossibly brief moments before annihilating each other. These quantum fluctuations have energy, usually positive energy. But under specific conditions, you can create regions with energy density lower than the vacuum. Negative energy. The problem is scale. Quantum effects that produce negative energy work at microscopic scales, nanometers, individual particles, creating enough negative energy to warp spacetime around a spacecraft. That's like trying to boil the ocean one molecule at a time. Technically possible in principle, practically impossible in reality. The gap between the equations allow it, and we can build it, spans the entire universe. Scientists didn't give up. They couldn't. The Alcubierre drive represented the first mathematically valid, faster-than-light travel method. It wasn't speculation. It was a solution to Einstein's equations. So researchers started looking for ways to reduce the energy requirements, to make the impossible merely incredibly difficult. They found some. Changes to the shape of the warp bubble reduced energy needs. Optimizing the thickness of the bubble boundary helped. Advanced calculations suggested maybe you didn't need Jupiter's mass. Maybe you only needed an asteroid's mass. Maybe just a large spacecraft's mass. The number kept dropping as people refined the mathematics, but it never dropped to zero. It never became easy, and it never stopped requiring negative energy. The Casimir effect and proof of negative energy. Here's where theory meets experiment, where the abstract mathematics of negative energy becomes measurable reality. In 19, Dutch physicist Hendrik Casimir predicted something bizarre. Place two uncharged metal plates extremely close together in a vacuum, and they'll attract each other, not through gravity, not through electromagnetism, through quantum vacuum fluctuations creating negative energy pressure. The effect is tiny, unimaginably tiny. You need plates separated by distances measured in nanometers, billionths of a meter. At those scales, quantum effects dominate. Virtual particles appear and disappear in the vacuum between the plates. But here's the trick. Long wavelength, virtual particles can't fit between the plates. They're excluded. Only short wavelength particles fit. This creates an imbalance. More virtual particles outside the plates than between them. That imbalance creates pressure, negative pressure. The plates get pushed together. In 1996, physicist Steve Lamero measured the Casimir effect with unprecedented precision. He placed gold-coated plates in a vacuum chamber and measured the force between them as he varied the separation. The results matched Casimir's predictions perfectly. Negative energy exists. We can create it. We can measure it. It's real. But the scale, that's the problem. The Casimir effect produces negative energy measurable in nanonewtons. That's billionths of a newton. A newton is already a small force, roughly the weight of an apple. A nanonewton is a billionth of that. You'd need to scale the Casimir effect up by a factor of roughly 10 to the power of 40 to generate enough negative energy for an Alcubierre drive. That's a 1 followed by 40 zeros. A number so large it's essentially meaningless. Still, the principle is proven. Negative energy exists. We've created it in laboratories. It's not fantasy. It's not speculation. It's measured experimental reality. The question isn't whether negative energy is possible. The question is whether we can produce it in useful quantities. And that question remains unanswered. Some physicists proposed alternatives. Maybe we don't need exotic matter. Maybe we can use regular matter in exotic configurations. Maybe there are other space-time geometries that achieve similar results with less demanding energy requirements. These ideas remain theoretical, unproven, speculative, but they keep the door open. They prevent the Alcubierre drive from being definitively impossible. Think about what this means. We have a blueprint for faster-than-light travel. The mathematics works. The physics allows it. We've even proven that the key ingredient negative energy exists. We're not missing some fundamental piece of theory. We're missing engineering capability. The gap between where we are and where we need to be is technological, not theoretical, reducing energy requirements and the future. After Alcubierre's original paper, Physicists attacked the problem from every angle. How do you reduce the energy requirements? How do you make this remotely feasible? The answers came slowly, but they came. First breakthrough changed the bubble shape. Alcubierre's original design used a symmetric bubble. Same radius in all directions. But you don't need that. Make the bubble thinner. Flatten it like a disk rather than a sphere. That reduces volume, which reduces energy requirements. Not by a little, by orders of magnitude. Suddenly you need less than Jupiter's mass. Maybe only Saturn's mass. Progress. Second breakthrough. Optimize the transition region. The boundary between normal space inside the bubble and warped space outside doesn't need to be sharp. Make it gradual, a smooth transition rather than an abrupt shift. That further reduces energy requirements. Now you're down to planetary mass rather than gas, giant mass. Still absurd, but less absurd. Third breakthrough. Adjust the velocity profile. How fast does the warping need to occur? Can you ramp up gradually rather than instantly? Yes. And that helps too. Each refinement shaves another order of magnitude off the energy requirements. From Jupiter to asteroid. From asteroid to spacecraft. From spacecraft to maybe just a fuel tank. By the early 2000s, some calculations suggested you might only need several hundred kilograms of negative energy. Still an enormous challenge. Still requiring physics we don't fully understand, but no longer requiring planet mass quantities. The impossible became merely stupidly difficult, which, in physics, counts as progress. Engineers started thinking seriously about implementation. Not we'll build this next year. More like if we dedicate centuries to solving this problem, maybe our descendants could attempt it. The conversation shifted from pure theory to speculative engineering. What materials could contain negative energy? How would you generate it? How would you shape the warp field? How would you navigate inside a bubble where you can't see outside clearly? These questions remain largely unanswered, but they're the right questions. They're engineering questions, not physics questions. And engineering problems eventually get solved. Maybe not quickly, maybe not easily. But humans have a track record of building things that initially seemed impossible, heavier than our flight. Nuclear reactors, computers, spacecraft, things that violate our intuitive understanding of what's possible but obey the laws of physics. The Alcubierre drive obeys the laws of physics. Barely, it exploits a loophole in Einstein's equations. It requires exotic physics we've barely begun to understand. It needs technology we won't have for centuries, maybe millennia. But it's not forbidden. It's not impossible, in principle. It's just really, really hard, which means humanity might eventually crack it. Some future civilization might look back at our era and laugh at how primitive we were, how we thought negative energy production was difficult, how we struggled with concepts they mastered as children. Or maybe they'll look back and understand exactly why we found it so challenging. Why the gap between theory and implementation proved so vast. The blueprint exists, but materials don't. Here's where we stand today. We have detailed mathematical descriptions of how to warp space-time for faster-than-light travel. We have refinements that reduce energy requirements by 30 or 40 orders of magnitude from the original proposals. We have experimental proof that negative energy exists and can be created in laboratory conditions. We have a roadmap, but we don't have the materials. We can create nanoscopic amounts of negative energy between parallel plates. We need macroscopic amounts, kilograms of it, tons of it, shaped and directed with precision, stable enough to maintain for hours or days. controllable enough to turn on and off safely. No known technology does this. No proposed technology does this. We're not close. We're not even in the same ballpark. The gap between a Casimir effect experiment and a working warp drive is like the gap between rubbing sticks together and building a nuclear fusion reactor. Technically, both involve releasing energy, but the engineering challenges might as well be infinite. Some physicists remain optimistic. They point out that every impossible technology eventually became possible. Powered flight seemed impossible until the Wright brothers did it. Space travel seemed impossible until Sputnik. Splitting the atom seemed impossible until Manhattan Project. Maybe negative energy production will follow the same pattern. Impossible until suddenly it isn't. Others are more skeptical. They note that all those previous impossibilities were engineering challenges. We knew the physics worked. We just needed better engineering. The Alcubierre drive might be different. We know the basic physics works, but we don't know if the exotic physics scales up. Quantum effects that work at nanometer scales might not work at meter scales. The universe might have built-in limitations we haven't discovered yet. Both groups agree on one thing. We need to keep researching, keep refining the mathematics, keep exploring quantum field theory, keep searching for ways to produce and control negative energy, because even if the Alcubierre drive proves impossible, the research might lead somewhere else. Some other method of faster-than-light travel, some other exploitation of space-time geometry, some other loophole we haven't imagined yet. But there's a darker question we haven't addressed. Even if we solve the engineering, even if we build a working warp drive, even if we can travel faster than light without technically violating Einstein's equations, what happens to causality? What happens to cause and effect? What happens when we can send messages that arrive before they're sent? That's the final horror, the ultimate price for exceeding light speed. Not energy requirements, not engineering challenges. The complete destruction of time's arrow, the shattering of causality itself. And that might be why the universe makes faster-than-light travel so monumentally difficult. Not because it's impossible, because it's dangerous, because it threatens the foundation of reality. Right now, you're standing at reality's most dangerous cliff. We've explored the ship, witnessed time freeze, discovered the warp drive blueprint, but here's the terrifying truth. Breaking light speed doesn't just bend physics. It shatters the fundamental logic holding existence together. Light speed is the speed of reality itself. Scientists thought light speed was arbitrary. They were catastrophically wrong. Light speed isn't a speed limit for objects. It's the speed at which cause creates effect. It's the universal refresh rate of reality. Every action sends information through space-time at exactly light speed. You flip a switch. Signal travels at light speed. Bulb lights up. Cause, then effect. Always in that order, but exceed light speed. And from certain reference frames, you travel backward in time. Send a message faster than light, and the response arrives before you sent it. Think about what that means. You ask a question Monday. The answer comes back Sunday. Before you asked, which came first? The question that caused the answer, or the answer that existed before its cause? Your brain rejects this because accepting it means reality makes no sense. The grandfather paradox reveals universe's deepest fear. You build a time machine. Travel to 1920. Prevent your grandfather from meeting your grandmother. You were never born. But if you were never born, you couldn't travel back. So your grandfather meets your grandmother. So you are born. So you travel back. The loop never ends. The universe demands logical consistency. Event A must lead to event B. Event B cannot erase event A if faster than light travel allows time travel. Causality collapses. Events happen before their causes. You become your own ancestor. Reality implodes into contradictory chaos. Stephen Hawking proposed the chronology protection conjecture. The universe protects its timeline at all costs. It would rather make faster than light travel fundamentally impossible than allow history to unravel. Scientists ran thousands of simulations. Every single one produced closed time-like curves, time circles that trap you in your own past. One spacecraft travels faster than light for 10 seconds. When it stops, local time has rewound 3 hours. The crew watches their own launch happen again, both true and false simultaneously. Reality fractures. Maybe lightspeed is protection, not prison. Here's the shift. Lightspeed isn't keeping us in. It's keeping something else out. Times collapse. Every moment in your life happens in order. Wake up, eat, work, home, cause, effect, cause, effect. Lightspeed ensures that chain never breaks. Exceed it, and the chain tangles. Creates knots where yesterday affects tomorrow, which changes today. Your consciousness depends on experiencing moments in sequence. Without causality's protection, you might not be you anymore. The universe drew a line. Lightspeed marks the boundary between what we can reach and what we can only dream about, between exploration and paradox, between adventure and the unraveling of cause and effect. Right now, light races across the void, moving as fast as anything can move, and it will never go faster. That is the universe's final word, unless we find a way to make it say something else. Would you risk everything to touch the stars beyond, or accept that some boundaries exist because crossing them destroys existence itself? The line stands, the barrier holds, and maybe that's exactly how it should be.